Well, we've made it to the last section that I'm going to cover on chapter 4, and it's still looking at probability. And we're going to be talking in detail about complements, conditional probability, and we don't really cover Bayes' theorem, but this one's important because of its at least one. So we consider the probability of at least, meaning if I get at least one and the set has five, then I could also have two or three or four or five of the elements. At least means that I can have more than the one I needed. So the at least is one of those conditions where we quantify the probability to include many options. And this is the important aspect of this one. So we begin with A getting at least one of an event and not A getting none of the events. So in this case, uh, we're looking at the probability of a specific at least one, and then the probability of not getting any. And we're using this one to find this one. So it's going to be easy. I'll do the best I can to clarify anything that might upset us. The probability that an event A does not occur is the one with the bar. And this one means zero, okay? And in most cases, we subtract the results from one, that is, evaluate the expression. So we say if we want at least one, then what we do is take one minus the probability of not having that event occur. That means that it will accumulate all of the probabilities of those other conditions. And this makes it very easy to calculate. So here we go on this particular item, the complement of at least one. So let's see what we can do. So we have to let A equal, the subject is telling the truth. And event B is a polygraph test that indicates that the subject is lying. So, using your own words to translate the notation of probability of A such that, a probability of B such that A occurs. So, this is a conditional understanding. I haven't talked about it, but I'm going to do this particular one. And what this does is center the focus of the structure of the probability to a subset, So what this says is event A is telling the truth. Event B is lying. All right, now let's read what it says. The probability of B, okay? So we're saying the probability, the subject is lying. Okay, and that's such that A, given the subject is telling the truth. So here we're talking about a table where they do those polygraphs and figure out if they think you're telling the truth or lying. Again, they're measuring a parameter of pulse rates and other aspects of blood pressure and whatnot that give them the idea of uncertainty on your part and therefore making that conditional suggestion. But I'm going to come back to this in our lecture. All right, let's do this example. Based on a poll, 64% of internet users are careful about personal information when using public Wi-Fi hotspots. What is the probability that among 4 randomly selected internet users, at least one is careful about their personal information? So here I'm going to introduce certain things so that we can understand what we're looking at. So our sample, our N, is going to be from, let's see, what was it? 4 internet users. And we want at least one. All right. And we know that the probability is probability of public Wi-Fi carefulness or is 64%. So if we want at least one, we can have 1 or 2 or 3. But the idea of the probability that at least one of the 4 are careful when using public Wi-Fi. Okay, so the at least one says that I do 1 minus the probability of not being careful, right? All right. So, well, how do I get that value? Well, if careful is 64, then not careful is 1 minus that 64%, which would make it 36. All right. So now I can do what this is. And we have to understand that the repetition of the value is to the number that we need, which is the number of the N. All right, because the at least says that none of them are careful. None are careful. So that would be decimal 36 times decimal 36 and so on 4 times. So let's do the math. It should be small, shouldn't it? Oh, I'm sorry. And we're going to use 3 decimal places because it's so large a percentage of at least one of them being extra careful. So the probability of careful Wi-Fi users, careful, public Wi-Fi, is going to be 0.983. Highly, highly possible to get at least one of those interviewed to be careful about their Wi-Fi. All right. Now, it asks, and of course, you know, when we do statistics, we're always making uh, determinations, and I've always used the word inferences. So here we have the question they pose to us. How is the result affected by the additional information that the survey subjects volunteered to respond? Well, in chapter 1, we knew that this one is a voluntary response and leads to bias. In other words, you choose to respond. Well, people that are definitely going to not give out information on a public Wi-Fi are going to respond and saying, heck no, I'm not doing that. Whereas the ones that do say, I don't even care. So it might lead to a bias, a misconception of the data. So we can say the data collected may not fully represent all public Wi-Fi users because of this voluntary response, and draws questions on how you collected the data. All right, so let's do another example. All right, so on this one, it says identify, ooh, what happened here? Let me look at my notes and find out what happened. Well, that one is cut off. Okay, so I can't do it. Uh, well, I can't do that one because I don't have the tape. So we're going to take off to conditional probability. Conditional is what I did on the very first example, and that had to do with the probability obtained with the additional information from another event has already occurred. And this is usually a table of collected data that has than one category distinction. It's not it's numeric, so it's not a category like name, but a distinction in numbers. So that's conditional, and that's event A such that given B. So let's look at this. examples, and we'll have them now mixed up. So we'll have part of the first part and part of the second part, because somehow my notes got a little bit mixed up, which I'm upset about. Event A is equals the subject is telling the truth. In event B, the polygraph test indicates it's lying. We did this one, so you can tell something happened here. Okay, here we go. We'll do this one. In an experiment, college students were given either 4 quarters or a dollar bill, and they could either keep the money or spend it on gum. The results are summarized in a table. These studies are always done as to how people nowadays, everybody has debit cards, which money will probably go by the wayside. But these are investigations about change. So we have two structures here. Students given 4 quarters and students given a dollar bill. 34 were given quarters and purchased gum. 15 of the total kept the money, the 4 quarters. Students given the dollar bill, 19 purchased gum and 32 kept the dollar bill. Automatically, you can see the connection of choice. So it says, now we're going to add our column, or we're going to add our categories. So let me get my calculator. Okay, so we have 100 subjects that were given this stuff. And we're going to find the probability of randomly selecting a student who spent the money given. All right. So this means conditional, given that the student was given 4 quarters. All right. So we want find the probability of randomly selecting a student who spent the money. So they purchased gum. Given that they were given 4 quarters. All right. All right. So we're going to have, let me write it down. Probability. There we go. Spent money on gum. Such that given 4 quarters. All right. So we had 34 under that heading, under that explicit subgroup. We had 34 out of the 49, which is given, they were given 4 quarters. So now we're going to find the probability using our calculator. And we have 6, 9, 3, 8, 7, 7, etc. And we want to do 3 decimal places. We're rounding correctly. So we have almost 70% spent the quarters. Now we're given another question. And it says, find the probability of randomly selecting a student who kept the money. Okay, so we're going to, a student kept the money. Given that, okay, now that we have the condition, the student was given 4 quarters. All right. So we're going to have the probability kept money such that they were given 4/4. All right, well, this one is the remaining item of that condition. It's 15. I mean, sorry, yeah, 15 out of that 49 of that condition. And that gave us the value of, so on. We're going to do 3 decimal places. And you can see if we added them up, we would have gotten 100%. And it doesn't always work that way, but in some of these problems, you can see the connection. So that gave you the first exposure to given. And the key of the language is given. Given. Well, we have another table, and we're going to add some columns here. Got yes and no. Oops. 135 and 6. Uh, 36 and 123. All right, so, and it looks like 300, but I'm going to do the math. 300 in our sample space. All right, so let's read. The data represents the results of a test for a certain disease. Assume one individual from the group is randomly selected. Find the probability of getting someone who tested negative, all right, tested negative, given he or she did not have the disease. Okay, well, that's interesting in itself. Okay, so we have positive and negative on the horizontal, and verticals we have yes, had the disease, no, did not have the disease. So they want the probability. Let me make some room. Tested negative, given did not have disease. All right. Well, we can see we're going to need this number right here as tested negative, but did not have the disease. So this is did not have the disease, no disease. Okay, so that's this part right here. Now, tested negative, so that's at 123, and did not have the disease. Oh, wait, what do I have? Tested negative and did not have the disease. Yeah, that's what it is. Very, very high number. They tested negative, did not have a disease. Ooh, hold on. Tested negative, which is a 129, but did not have the disease. No, I got that right. Got it. Had to think. Easy to get mixed up, isn't it? right. Pretty sure that the test, if you can test negative, tested negative, and did not have the disease, and no, did not have the disease. So that is good. All right, now we're going to this one, and we're going to assume that there is 11% rate of a disk drive failure in a year. Disk drive failure. So that's our probability. Yeah, that you keep all that stuff and then it doesn't work. So we're going to do the A. If all your computer data is stored on a hard disk drive with a copy stored on a second hard disk drive, what is the probability that during the year you can avoid catastrophe with at least one working? Okay, so here we have two of them, and we want working. All right, well, this is failure. So we're going to say 1 minus 11 hundredths squared because we have two of the disk drives. So it says at least two hard drives working. So we're going to have the not of it, which gave us the information. Which we knew was going to be a very large possibility that at least one of your items would work. And that's what we would put down. It's almost 100%, isn't it? This is for the A. These of all your computer data are stored on three independent hard disk drives. What is the probability that during the year you can avoid catastrophe with at least one working? Now we have the cloud, so this is pretty much a mute point. But again, there is information that is stored for backup purposes. So this would be 11 to the 3 because there, this case, we have 3 disk drives. So even having one backup is security enough, and having 3 is super security. So that completes this section. It's very short. You only have about 8 problems. I've just getting you exposed to this. I am not making you a probability expert. But we are going to use probability from this point on, understanding of the other concepts. So getting a handle on this stuff is better for you. Thank you for listening. Do your homework.